Is it because you're
The phone is ringing.
Miss
Miss G, do you want someone to answer the phone?
Yeah.
Yeah, do you want to go see the students?
I do. So mine's
Hi, Miss D'Israel. Students meeting.
There you go. I was just.
Okay. Okay, yes ma'am. Okay, thank you. Katrina needs to be dismissed at 11:45 to pick up a note.
It's a bad sign. No use code for.
Can you watch the video?
Yeah.
I didn't watch last week's video.
Alright, kiddos, do you at least agree with the picture that I drew in that I went parallel to the axis of revolution, I drew my cylinder, there's an R, and there's an H for us to identify. Corey.
Why did you use shells circles?
If you were to do this, number one, it's going to have to be washer, because it's not flush. And number two, you're going to have to do top minus bottom, top minus, I think shell is just easier to set up as an integral to solve. But it doesn't mean that you're wrong. So I'm starting with shell.
That was the question.
I'm starting with shell. Yeah, explain your reasoning. So I'm showing you shell, and then let me show you this, and then we'll compare. So here's our shell. I went parallel. Okay. Question. For parallel, question. Hold on. First of all, is this going to be a dx or a dy? dy. I need to put thickness to my shell. So therefore, I need to solve this in terms of x, right? So x is equal to, let's see, plus x minus 4 minus y minus 2 quantity squared. You guys agree? And that defines the entire curve, right? It's not like a weird plus or minus square root thing. For washers, you have to solve for y plus or minus square root thing. You have to define it in terms of two different functions and keep them straight. Not impossible, but not fun either.
Nope.
So then we do shell. Guys, what's our volume formula for shell?
2 pi
integral.
We're going to go y1 to y2, and then we're going to do somehow r in terms of y to h in terms of y dy. But isn't r just going to be, y is the height, right? So y minus 0, because the axis hasn't moved anywhere. So I can go ahead and say, I'm going to plug in 2 pi. I'm going to have my y minus 0, which is just y, but what's my height going to be?
The formula.
It's going to be x. This one's going to correspond to x minus 0, this one's going to correspond to y minus 0, but I can't have an x in my expression, so instead I'm going to plug in the function. So I'm going to have times 4 minus y minus 2 quantity squared dy. What are my y bounds? We have to find them naturally, but we can set this x equal to 0, right? And it's going to equal 0 at 0, because then that's squared, and 4 minus 4 is 4. And then at 4, 4 minus 2, 2 squared is 4, 4 minus 4, good. At 0 and at 4, if we were to solve. It's as easy as that. If you were to do discs, not impossible, but first of all, it would need to be a washer, not a disc. First of all, it has to be a washer, not a disc. Second of all, I have to do 2 x values, which I would have to, wait, how am I going to find the x value? I'm going to start at 0. But where does that end? I'm thinking about the natural domain of my function. This is going to end up needing to be solved for y instead. So y is going to equal 2 plus or minus the square root of 4 minus x, which has a natural domain of 4, which is why I'm going to have to do it 4. I'm going to have to do big R squared minus little r squared with dx. And I have to think of big R squared will be from the outermost down to the axis, little r squared, the hollow, the edge of the hollow to the axis. This guy is going to be the positive square root piece because it's the top of my parabolic curve. So that's going to end up being 2 plus the square root of 4 minus x quantity squared, technically minus 0. Minus, now I'm going to have the bottom of my curve, 2 minus the square root of 4 minus x quantity squared. Which one looks more fun to solve? I don't know, I'm still going with that one. But, is this one possible? Yes. Are we gonna solve for the exact same thing? You plug both of them into the calculator, even if you make both their variables x. Yes. They'll both be the same. And we'll be totally fine. Okay, number next one. Where are we supposed to be going about?
Y, x equals 4.
Hey kiddos, how could you have gotten the graph of this function without? Yeah, couldn't you maybe have just found the intersections and seen if that helped? Maybe go ahead and factor out an x, 2 minus x. Where are your intersections? You know it's a downwards parabola. The intersections are going to be at 0 and 2. That helps a little bit. So x equals 4 is out here, yeah? Aren't I going parallel? Which has a thickness of? And then I'm rotating around. Now, can't quite show the whole thing, but I can show part of it. Isn't my radius going to be? Ooh, that's my radius. Isn't my height going to be? Height looks a lot like just the y value, right? Okay. So I have v is equal to 2 pi. And I'm now doing x1 to x2. R of x, h of x, dx. H looks an awful lot like just the y value, because it's off the axis, which is nice. If this was ever moved up or shifted up, I'd have to do y minus, maybe like if it was up at 1, y minus 1, or if it was down 1, y minus negative 1. This should be y minus 0. What's my r going to equal? 4 take away the x. Remember, the x is coming from the origin, and this whole thing is 4. I have to do 4 minus x to get my radius, which is how we end up with v is equal to 2 pi. x1 to x2 is from 0 to 2, right? R of x is 4 minus x. H is just going to be, wait. Hold on, what am I in terms of? Okay, so that's all right, but when I go to do the y, that doesn't work. What do I need to plug in for my y? Exactly. I know, set up and solve, whatever, you guys keep solving. But because my region is from x equals 0 to 2. Yeah, it's my region.
So, depending on which revolve around, that'll affect only r, essentially, unless it's like translated.
Essentially, yeah. Because if you're revolving around horizontal, that's going to affect your r, which now has to do with y's, but either way, yeah, it only affects your r, and then this way it will affect your r's in terms of that. Hang on, Gabby.
Why is the radius 4 minus x?
Does it make sense, the picture at least? I did a parallel slice and I'm revolving. Okay. Radius always goes, and that's even in distant washers, from the axis out to the slice. If you're looking at the radius, it's a right-left radius, right? Don't we always do right minus left? Who's on our right? Sorry, I didn't label it. Who's on our right? 4. And who's on our left? X. So when you hit, you could think about it, if it helps, you can say I hit at an xy, where this is my x and that is my y. Okay. So then that's how I was able to say the height was my y, and then this, that's not my radius is here. So it's going to be the 4, take away the x. That's what we're going to do. So we can say this is our 4 minus x. That's how I was able to do it. Okay. When you have axis of revolution for any figure, it's going to somehow factor into your r's, right? And then if a region gets shifted up or down off an axis, then it's going to affect your height. Well, unless you're oriented the other direction. But just be aware. Just be aware of how funny circumstances might change up the expressions a little bit. But guys, is the formula still at the core the same? Yeah. Shell method. I need volume equals from A to B of R of X, H of X dx, or R of Y, H of Y dy. And we always have to remember our representative slice is always going to be parashell, right? Parallel. to the axis of revolution. How is that different than with discs and washers? We've been doing a lot of shells. Let's go back for just a second. Pause. You guys did a lot of work with discs and washers, right? Right here, these 4 problems. How were we always slicing? Parallel and then rotating? No. We were slicing straight down and we were having a circular slice. So our straight down was going to be, or our straight across. We're always going perpendicular. Does that make sense? So slicing perpendicular for discs. Flush, disc, pi r squared. Hollow, not flush, washers. Perpendicular, and then giving it a thickness of dy. Perpendicular, giving it a thickness of dy. But with shell method, what's different? We're slicing parallel and giving it a thickness of what it has. Kiddos, that is the end of section 8.3. Oh, I just went way too far. Wow. Sorry. Section 8.4. Ah, there are 2 endeavors. My goal is for us to get through both endeavors today. Maybe not the full theory behind what they are and how they show up, but my goal is to get through both endeavors today because I would love to be able to have tomorrow still be our review where we're going over homework questions. You guys have already, or you will have been able to check the evens. And then come to me with questions. We might have to finish up an example or 2 tomorrow in 8.4. We might need to. But let's see if we can get both the endeavors down so you have both the formulas. I think we're on endeavor 9 and 10. Does that sound right?
Yeah.
The 7 we already had done. 8 with shells. Yeah.
Oh wait. I think it's
No,
8,
7
9,
is shells.
7.
Oh, 7 with shells. What does it say with shells? So our class is going to be endeavor number 8. It is kind of small though. If you guys don't mind, maybe I'll zoom in. Single page. It's getting a little small. Sorry, it's not happy. Okay. 2 things. Arc length. That's the first endeavor. Endeavor 8. And then surfaces of revolution. Endeavor 9. We're going to be able to use integration to find surface area of any shape. That's just the ones that we've learned from geometry. As you guys, let me start over here. As you guys are writing that down, our designer over at Impact Shirts left and went to a better job. I don't know exactly what that means. The guy, the head of the company, he was like, oh, yeah, he switched jobs into something that he loves, and I think it's even like closer to family or something. They're in a totally different city. Anyway, long story short, they have our design, just our guy, our contact guy, just kind of didn't tell me he was gone. And he's done a lot of good work, so I don't want to brag on him at all. It was a good thing for him, et cetera, et cetera. However, the new guy, he did go ahead and get in contact with me. He's like, hey, follow up. So here's what I'm passing around right now. I'm passing around, you guys basically know the design. I'm adding in parametric functions, first, second derivative right underneath the yes, it is rocket science because you can parametrically, they do parametrically trace the, I cannot get the terminology right now. The trajectories of the rockets, there we go. So some people want some math, we're just going to throw in a first, second derivative of a parametric right underneath the yes, it is rocket science in the back. You can give your size, what you would want. You can give your type, crew or fitted, long t-shirt or short sleeve t-shirt. Because technically the designs will all be the same on any of them, so it doesn't really matter the item, just depending on what you choose, you might pay a little more. I think what he has right now for us is a hooded sweatshirt, which is around $30 if we have at least 12. Because we can put tons and tons and tons of wording everywhere, so that would be nice. And the logo on the sleeve is small. It'll go in a t-shirt, it'll go in a sweatshirt. So you can choose basically whatever type you want. Just think if you don't get the hooded, it should be a little bit cheaper. You can also, because I had some people come ask me, you can also, if you really want one, you can also put down that you want a white sweatshirt. You'll just have to have your own design, and it'll probably be at least 10 to 20 bucks more. But if you don't care, I don't care either, because as long as we have 12 of the other items, we should be good. And I think there are only a select few that really want white, so it's white or black. If you guys can fill it out, I can get in numbers. Sorry for the delay, I just didn't realize our guide. So lost so much. Okay. Yeah. My guess is probably somewhere around 2022. That's my guess. Because the sweatshirt, the hooded he said was around 30, so it should be a little bit cheaper than that. Okay, I'll get you more final when we put it in numbers. Okay, kiddos, what we're doing, arc length. There is a snazzy word that we don't necessarily use it over the AP so much, I haven't really seen them use it. However, it is helpful for our purposes. Basically, we can only find arc length of rectifiable curves, which have a finite arc length. If they have an infinite arc length, that's going to be a little bit harder. But in order to have or to be rectifiable, there are a couple conditions. Nice thing is it's not a forever card. I'm just letting you know that not everything has a finite arc length. If f prime is continuous on A to B, if f prime is continuous, aka if f is differentiable, then f is rectifiable. Or you can also say continuously differentiable or smooth curve. So no sharp points or vertical tangent lines. If you guys notice, if I was to use the distance between 2 points formula, distance. Okay, the distance between 2 points formula. Wouldn't that just be making a secant line? Right? F B minus F over B minus A. That would be slope. If I was to use it in x2 minus x1 all over y2, sorry, x2 minus x1, I can't do this, squared, plus y2 minus y1 squared, square root. I could find the distance diagonally. The question, is that going to be super helpful as far as getting an arc length? Would it approximate? Could it approximate? Yes. But am I going to be able to throw that into an integral? No, because I have no expression that I can have be basically my differential that I can have getting infinitesimally smaller than etc. So instead of using just the simple distance formula, maybe we should instead think about this curve and think about the A and B. So instead of thinking about the distance between A and B, maybe I should think about going on the tangent line instead. So if I go on the tangent line, then I could go ahead and think about dy and dx. Instead of thinking about b minus a and instead of thinking about f of b minus f of a, maybe I could think about dy and dx instead. And then maybe I can have dx approach 0, aka delta x approach 0, and then maybe I can, so I'm still going to be using the distance formula, but instead of thinking about the distances between the 2 points from the 2 function points, I'm instead thinking about the distance formula, but using the differential equation because we're using the differentials because I want to use the tangent line instead. Now, as I go to use the tangent line, hold on, how are we going to get this? There's a few different ways of thinking about it. But here's one way. If I was to go ahead and plug in as is, similar to the distance formula over here, wouldn't I have to do dx quantity squared plus dy quantity squared? Can I throw that in an integral the way it is?
No.
Not so much. Don't I need a differential to be on the outside?
Yeah.
Okay, so what could I do? What if I were to divide everybody by dx squared? And I could multiply top and bottom by dx squared. Is that technically legal? Multiplying top and bottom, I'm just multiplying by 1 creatively, right? Okay, so then I could go ahead and say, let's see if I can make this a little bigger. I could then go ahead and pull out the dx squared on top. Factor out, because they both got dx squareds on top that are somewhat, I don't know, unrelated. What's dx squared over dx squared? 1. What's dy squared over dx squared?
dy. Isn't it just dy?
dy dx
Squared.
squared. What can we do with the square root of dx squared?
Take it out. Oh, you.
Is that ready to integrate?
Yes.
Ooh, Gerber, sorry, endeavor card number 8. To find the arc length of a function, you can either do it in terms of dx or dy. Ooh. snap. Wait. There's no condition? No. Horizontal vertical axis? No. Perpendicular to? No. We're not slicing. We can use whichever one is nicer for the given information. Literally, there is no condition that needs to be true besides the fact that you can somehow represent the function and its derivative in terms of x, or the function and its derivative in terms of y. Arc length is super nice in the sense that the only thing that will lead you in the direction of using or plugging in terms of x or plugging in terms of y is whichever one is easier for the equations that you're given. For disks and washers, you have to make sure that based on your axis of revolution, you are going perpendicular. For shells, you have to make sure that based on the axis of revolution, you are going parallel for your dx or for your dy. For cross sections, you have to make sure that you're assigning the proper thickness to how you are slicing perpendicular to the x or to the y, to a horizontal or to a vertical. But for arc length, just plug it in. Okay, the interval from a to b, they're going to have to both be x's if you're doing in terms of x, 1 plus the derivative squared dx. So we have to find derivatives first and then plug in and solve. How nice are these formulas? Pretty nice. Pretty nice as far as the work that is required. You give a couple more seconds. Are you guys to the point where you know how the formulas are operating? If I zoom out, you can still understand what you're supposed to be writing? Mm-hmm. Pretty close.
I think so.
Oh, I erased my graph. You can't see my interval. Well, that's fun. Okay, let me just get rid of this then. That's why you keep it. It's not showing it to you. I don't really want to graph my cubic function. Let's do. Okay, we're gonna do for number 4. Make a what? Yeah, you could.
Should you start by dividing?
I want you to take the derivative first.
Oh,
Yeah.
you can just do that.
I think that's pretty important.
So that'd be what, 1/2 x squared? Bring down the 3, 1 squared.
Oh, yeah.
Why do we not need quotient rule?
Oh,
Divided by 6 is 1/6. Good, it's a constant in the denominator. What can we do here?
1 over.
1 over.
Wouldn't you do
Negative 1 over.
1/2 times x?
1/2 No, it's bottom squared.
You haven't derived it, so.
1/2 times 1 over.
Can I make this 1/6 x cubed plus 1/2 times 1 over x?
Wouldn't that be 1/2 of them?
You're in Direct.
Yeah, I get that.
Direct.
It's been so long.
So it's x to the -1, bring down the -1, make it -2. You could also do quotient rule. Bottom d top would be 0 minus top d bottom would be 2. All over bottom squared, the 2 over 4 reduces to 1 over 2. Either way, we end up with x squared over 2 minus 1 over 2x squared. Where am I putting that derivative?
It's under the square root of the 1 plus in front of it.
Yep, so I can say that arc length, which they call little s, just like technically we called arc length back in pre-cal with the unit circle. S equals r times theta, arc length.
You're gonna go from 1 to 5. You're gonna go from 1 to 3. Square root of 1 plus
Yeah.
Oh, Yay! And we would use our calculators, but that's really long.
Yeah, is that?
Wait, are we allowed to just,
Actually, we have to have calculators. I don't think that's possible.
are we allowed to just, do we have to?
You would never give us a
Okay,
non-calculator.
it depends on the problem. I'm gonna have you guys go check it out in homework and see. You have your evens in the back, you have your odds in the back, and on CalChat, see what they do.
Or
Just kidding.
Yeah.
Just kidding. But can you check and see? If the answer's a decimal, what are you gonna be able to use? Your calculator. If it's nice and even, you can do it by hand. Can you figure out how? Number 15. What are you gonna do?
Drive.
Solve for y first. Never mind, you'll have to.
I said no.
You might have to.
Wires.
That's a little complicated.
Your
bounds are right as well.
If I bring down 3 halves, 3's cancel, I end up with 1 half, right?
Yes.
And then aren't I also gonna have a 2y? Times y squared plus 2, all to the 1 half. Those are gonna reduce. Yes, don't forget how to derive now that you've integrated a lot, okay? Double check we're good?
Yeah.
So now how am I gonna set up my integral for arc length?
You go from 0 to 4. 1 plus y times y squared plus 2 to the 1/2 y squared dy.
Are all of these gonna be impossible to solve by hand?
No,
Yes.
kind of.
Maybe?
Why do yourself?
Isn't a square root square just gonna cancel? So you just end up with y squared plus 2?
Yeah.
Easy.
Then couldn't you make that y to the 4th plus 2y squared plus 1? Then couldn't you just make that y squared plus 1 quantity squared?
What?
Oh,
Oh,
I factored. Then couldn't you do that and that?
Isn't
Yeah.
that the first one?
So are you telling me you can't integrate any of these by hand?
No.
We're
Better
just
not be.
lazy.
Yeah. Woo!
Okay,
To be honest, I would never.
we're gonna come back to this one in just a second. I want you guys to get your last endeavor card. Surfaces of revolution using frustums. Ooh. Frustums. You'll see the word in the middle. We're going to use frustums in order to get the surface area of other figures. I just want to let you guys get the formula down, because maybe you keep on going. Because our goal tomorrow is to finish examples of surface area. I think arc length is pretty self-explanatory. Good job when you get through that today. Tomorrow we're going to come in and do examples on surface area. If you want to try and get to those in your homework, that's a great idea. Finish up shells if you have not already. Start on 8.
Tomorrow? Are you gonna show this page tomorrow, please?
I'll actually probably have it on the screen when you come in. Just go ahead and start writing these. Sound good? This is endeavor number 9, the final endeavor of our semester.
Let's go.
About 28, 30. Did the special teacher keep it over?
Yeah, I got my food bag. I finally got
I'm
because all I have is this. But I can't hear this. Because Mr. Ken just keeps calling me.
Yeah, we have like 5 insurance for object.